welcome back, guys. Day 38. Awesome job today taking on that test on PVA. That will not be the last time we see PVA because we're going to solve problems once we know how to do integrals, but that'll be after Christmas. Today what we're going to look at are two very important topics that I kind of want to talk about together. I'm going to try and make this condense, and we'll dive deeper later in the week. But I want to talk about differentiability, and I want to talk about critical points. Both of these things are super, super important. So let's look at differentiability first. So when we talk about a function being differentiable, right? Let's say this. Let's say f is differentiable. F is differentiable. Right? When we look at that word differentiable, we see differentiate, which we should be thinking about derivatives, right? So this is related to derivatives. F is differentiable if we can take a derivative anywhere. So for something to be differentiable, right, on an interval, that means anywhere on that interval, we can find a derivative, right? We can find a slope of a tangent line. Okay? Most things that we look at over the years in math, almost everything has been differentiable. Just like almost everything has been continuous that we've looked at. But when you start to get into pre-calculus, and some of the stuff in Algebra 2 and even in Algebra 1 sometimes, we started to break continuity or break differentiability. These two topics tie together. So here's what we need to know. This is going to come in super handy, right? You know how when we have to prove using the IVT, we must state that a function is continuous first? Well, sometimes they don't say a function is continuous. They say a function is differentiable. This phrase is really, really important. Differentiability implies continuity. So if I said that f is differentiable everywhere, then it is implied we already know that f is continuous everywhere. So continuity, just as a reminder, meant that the graph was connected, right? There were no jumps, no holes, no removable discontinuities, no jump discontinuities, no infinite discontinuities, right? All those things. So if we say something is differentiable, we already know it's continuous, right? But it's going to be even more detailed than continuity was. If a function is differentiable, it means it is both, but here's how I think about it in kind of like layman's terms. I think about it as smooth and connected. So it's pretty cool. It's really smooth, right? It's smooth and connected. So connected would be the continuity part. Smooth means we don't have things like corners or cusps or things of that nature. Vertical tangents, right? So let's take a look at some examples here about smooth and connected. Okay. So if I had a function that looked like this, when I look at that function right there, I say, okay, that thing is definitely continuous, right? I don't see any holes. I don't see any jumps. I don't see any breaks. I don't see any vertical asymptotes, anything like that. So that thing is continuous. But notice how it's smooth everywhere too. Okay? There are no corners or cusps, right? So this graph would be differentiable. So there's an example of a differentiable graph. Let me show you another differentiable graph. Again, going back to that, right, when I take a look here, I could easily do a derivative anywhere on this function, right? I can find a slope of a tangent line here. I could find a slope of a tangent line here. I could find a slope of a tangent line here, right? I can find slopes of tangent lines anywhere on this graph, any point I pick, okay? So again, that's what I mean by you can take a derivative anywhere, okay? Here's another differentiable graph. Linear graphs are always differentiable. Okay, that thing is connected, right? It's a continuous graph, but I can find to a derivative anywhere, right? The derivative is simply going to match the slope of the line because it's linear. So linear functions are differentiable. In fact, all polynomials are differentiable. Okay. So if I had 8x to the 6th plus 3x squared minus 2, I know right away that's a polynomial. It's differentiable. I can do the derivative anywhere I want. Okay? Let's start looking at some things that have problems with differentiability. Okay? So here are our problems. This is where we fail differentiability. One type of thing is a corner. So if we have a corner, like let's say we graphed this function. If I graph this function, the absolute value of x minus 2 plus 2, right? That's the graph, the absolute value of x. It's shifted right to and up to. I shifted it just so we can see this a little bit better, so it's not right at the origin. This graph would look something like this. Okay. This graph is definitely continuous, right? It is connected all the way through. I could draw that without picking up my pen or pencil, okay? But there is a point in this graph where I am not going to be able to take a derivative, right? That point right at the bottom here, that vertex right here, that point fails differentiability. Because differentiability is such a long word, I often use diffability or diffable as an abbreviation. That point right there, I cannot draw a slope of a tangent line, right? Would it be like this? Would it be like this? Would it be like this? I don't know, but that point fails differentiability. So corners fail differentiability. Another thing that we see is what's called a cusp. Cusps follow or fail differentiability as well. Both corners and cusps are examples where we pass the conditions for continuity. However, we fail differentiability. Once again, that point there, right here, that fails differentiability. Okay? I can't do a tangent line slope here, right? Do I do it like this? Do I do it like this? Do I do it like this? I don't know. I can't do any of them because there are so many different options. Okay. Right at that point, I could not find the derivative. Any other point on that graph, on either one, I can easily find a tangent line. But a corner fails differentiability, a cusp fails differentiability. The other thing that we can have is called a vertical tangent. Vertical tangents fail differentiability as well. Think of this as like a terrace point flipped on its side. So if we see something like this, right, that looks like a terrace point, but it's flipped sideways, right? Right at that terrace point, there might be a case where the slope of this line is undefined, okay? And we can't report a slope of a tangent line if that slope is undefined. So right here, this fails diffable. This is not diffable. Okay. These aspects of graphs aren't super common, but they do happen, and we have to be aware of them. Okay. So vertical tangents, corners, and cusps all give us problems. Now, all three of those graphs I just showed you would all be considered continuous graphs. Okay. So they pass the threshold for continuity, but they are not differentiable. Okay. So they either have corners or cusps, so they're not smooth, or they have a piece of the graph that has a vertical tangent. Okay. Other things that will fail, discontinuities always fail differentiability. So if a function is discontinuous at a point, it is automatically not differentiable at that point either. So all of these points, whether it's a removable discontinuity, whether it's a jump discontinuity, or an infinite discontinuity, at all those places, I can't take a derivative. Okay? It has to be continuous. So differentiability implies continuity. So if something is not continuous, it's automatically not differentiable either. Works in the reverse way as well. If something is guaranteed to be differentiable, we know that for sure it is continuous. Okay? We'll look at an example. So let's take a look at the function f of x equals x to the 2/3. And I want to know, is this thing differentiable? Is it difficult? Okay. Well, let's take a look at the graph of x to the 2/3. So I'm going to call it my graph. I'm going to graph x to the 2/3. Go ahead and get your calculator out and do this with me. And let's take a look at what the graph of x to the 2/3 looks like. I'm going to clear all the other junk out of here. And I'm going to graph x to the 2/3. Okay. I'm going to hit zoom 6 to get kind of a nice standard look on here. So this is what this graph looks like. Now it looks pretty smooth. It's definitely connected here. This graph is definitely connected here. But it's kind of hard to tell what's happening right at 0 here. Again, this graph looks differentiable everywhere. The point I'm a little concerned with is around 0. So I'm going to do what's called a zoom box, number one. And I'm going to put a box around the middle so I can zoom in really close and see what it looks like. Normally, I don't like to use the zoom features on my calculator for solving test problems, but they are good for kind of exploring what things look like. So let's take a look up close. I'm going to box in that little area right around 0, 0 and see what this looks like. So what does that look like to you? Well, to me, it looks like a cusp, like what we looked at in the second graph of the failed differentiability ones. Let's see, can we confirm that we actually can't take a derivative at 0? Well, let's go back. Let's find f prime of x. Let's check f prime of 0. I want to check f prime of 0 and see if I can actually get an answer here or if I can't get an answer. Well, f prime of x, let's go back to our power rule, right? This is an ax to the n form. There's no chain rule here. There's no product rule, quotient rule. This is simply a power rule. So to do the derivative of x to the 2/3, I would get 2/3 x, and I got to reduce the power by 1, which would be negative 1/3. Simplifying this, I would call this 2 over 3x to the 1/3, which I would call 2 over 3 cubed root of x. So let's check out what f prime of 0 is. Well, f prime of 0 then would be 2 over 3 times the cubed root of 0. The cubed root of 0 is 0. Uh-oh, 2 over 0. Anytime I divide by 0, that is undefined. So f prime of x is undefined when x equals 0. Therefore, we know f is not differentiable at x equals 0. Okay? Now, here's where your calculator can run into problems. Okay? We proved that f prime of 0 does not exist. Now, your calculator, it's really good at doing numerical derivatives, except at points of discontinuities like this. It can really struggle because it just uses a program that estimates it. So let's think about what this would look like. Here's what I mean. If I do second calc dy dx, and I type in 0 for where I want to do my derivative at, it says dy dx equals 0. That is absolutely blatantly false. That is 100% not true. The derivative there does not equal 0. This is a place where sometimes when students use their calculator, they run into a problem. Okay? That is wrong. dy dx does not equal 0. dy dx is undefined. So your calculator at times can lie to you. Just be aware of that. Okay? All right. The next thing I want to talk about just briefly is critical point. A critical point is critical. Okay, so a bad pun, but it's also very true. Critical points are super, super, super important. Okay, so here's our definition. And this is where we need to be very, very careful. Most of the time, it's going to mean one thing, but this could mean either or here. Okay? F has a critical point. If I could spell, that would help. F has a critical point whenever f prime of x equals 0 or f prime of x is undefined. So f has a critical point whenever f prime of x equals 0 or f prime of x is undefined. That is our definition. Super, super, super important. So box that in your notes, put a highlighter around it, do whatever you do to be able to call your attention to that when you need it. Okay? So, in that last example, f of x equals x to the 2/3 power. F would have a critical point at x equals 0. Not because f prime of x equaled 0, but because f prime of x was undefined at that point. Okay, I'm just going to give one example quick, and then we're going to end this video. So I'm going to say this, f of x equals 4x squared minus 5x plus 2. My question is, what are the critical points of f? I'm going to say, what are the x values of the critical points? I'll use CP a lot. Okay. So what I want to do here is I want to find the critical points of f. Well, critical points by definition is when f prime of x equals 0 or f prime of x is undefined. So they both relate to f prime of x, so I need to first get to f prime of x. So first, go ahead and find f prime of x. It's a very simple power rule. We got 8x minus 5. Then I want to set f prime of x. Well, first off, this one. Is there any points of x where this thing is going to be undefined? No. Something's undefined when we divide by 0, or we try and take a log of 0, or something weird like that. Nothing here. F prime of x is never undefined. Right? X, the domain would be all real numbers. So what I want to do next is set my derivative f prime of x equal to 0 and solve. So when I solve this thing, I'm going to add 5 over. And the x value of my critical point would be 5/8. Okay? We're going to talk more in the next video, and we'll talk about it a little bit in class, about what critical points mean. Something really interesting happens on a graph at critical points. See if you can figure it out on your own. Okay, that's it for today's video. Again, nice job on your test today. Do chains. See ya. Bye.